Okay, let us begin the class. Refreshing, yeah. So refreshing. The first material is that I want to review the root locus. Yeah. For example, number 3 that we discussed on Monday. So you see, we have s times s plus 1 and in the denominator. And so what will be the open loop poles in this case?
0 and 1.
Correct. Then open loop zeros? Don't have, yeah. Asymptotes? Yeah, we have two asymptotes because 2 open loop poles minus 0 open loop 0. Yeah. So we have 2 asymptotes. And then what will be the angle of the asymptote? You just have to divide by 2, yeah. Why 2? This is the number of asymptote, yeah. The 2 below here is the number of asymptote. And then because it is 2, then we use k to be 0 and 1. Yeah. So the first asymptote will be 90 degree, and then the second asymptote will be 270 degree. Okay. And then we number the open loop poles and zeros on the real axis. So I will do it here. This is 0 minus 1. So we number it to be number 1. This is number 2. Number 1, number 2. And then after that, the location of root locus on the real axis will be on the left side of the odd number. Yeah. Okay. Find intersection of asymptote with the real axis. Yeah. Intersection of asymptotes. We use this formula. So we obtain the intersection to be here. Yeah. Minus half. But that's not necessarily the root locus, yeah, just the intersection between the asymptote and the real axis. So we know that root locus starts out from open loop poles and it will end at the asymptote, yeah. So it will go like this and then it has to split. Yeah. It is called breakaway in there, not split point. We are calling it a split point. We call it breakaway point. So to compute the breakaway point, we express the k. Yeah. So from the characteristic equation, we express the k. What's the k as a function of s? Okay, this is the k, and then we take the first derivative based on this equation, and then compute the roots of that equation. Okay, and we find out the breakaway point is also minus half over there. Yeah, then that means the root locus will be just like this. So it will go here and then going up or going down, doesn't matter. Yeah, that will be the root locus.
But is the point will be to the left?
No, in this case, it's the same.
Yeah,
If, yeah, okay.
How do we draw it? Is it on this, like this?
If let's say asymptote is here and then your breakaway point in there, usually it goes like this, yeah. So approaching asymptote is just like when you have a plateau in the time domain response, yeah. Okay, so going into plateau, don't make it stick like this and then straight. No, the approaching asymptote. Okay, but when we are drawing the root locus on our own, the most important thing is the sketch. Okay, not the accuracy of the root locus. It is the sketch, so that you can design the controller. Okay, is this okay? Yeah. Well, which is why on the homework for next week you are asked to draw the sketch of the root locus. It is not the exact root locus, just the, yeah, just a rough idea. based on the rules that we discussed. Okay. Another example 4. Can you do it? Yeah. Open loop pole 0 minus 1 minus 2. Okay. Open loop 0
Not available.
not available. Okay. Any asymptotes? 3. Okay. What will be the angle of asymptote in this case? 60. Ah, apa?
300 sama
180. Yeah. 60, 180, and 300. Okay. So you divide by 3 and then you use k to be 0, 1, and 2. Okay. Any question on this? Okay. So numbering the open loop poles and zeros on the real axis. Anyone want to try? Yeah, Nathan. Okay. Yeah, you get the point. Yeah, this is we don't have to write down on the paper. Yeah. And then minus 2. Okay. You number out. Yep. Yeah, that would be the location on the real axis. Yeah, that's correct. On the left of the real axis, yeah. And so, find intersection of asymptote with real axis. Anyone want to do it? Okay. Intersection. Okay. Intersection sigma A will be number of summation of the poles P pi, okay, minus summation of 0 z, yeah, divided by n minus m. Okay. Yeah. Yep. Minus 1. Okay. So that will be the intersection. Yeah. Yeah. If that's the intersection, how do you draw the asymptote?
So how to do the breaking points like
Yep. Huh?
breaking point. You want to do the breaking point.
Oh, wait. Okay. So breakaway point, Teddy first, yeah. Yeah, breakaway point. Say that again. Like this. Because the angle asymptote is 60 degree. 60 degree, yeah. Hold on, Teddy. Wait. Let me explain first. We have 3 asymptotes, right? The first one is this one. This is the second one. What do you think the third one? This one. Yeah, this is the third one. Okay. So this angle is 60 degree, and then this one 180, yeah, and then the third one 300. Okay.
Oh, and then we start from negative 1.
Yeah. We start the negative 1 because of the formula just now. But this is not the location of root locus, yeah. Not necessarily. Yeah. This is just the intersection. In fact, we will know from the breakaway point that they will split somewhere in the middle here, not from here. Okay. So Teddy, you can continue with the breakaway point. Yeah, characteristic. Sure. Okay, equal to
It's not real axis.
plus 2s. Okay, now you find out the first derivative.
We call it dk over ds.
Yeah, dk over ds. What's the dk means? What's your association with dk? Huh? Oh, I thought it's Donkey Kong.
Oh, sorry. Oh, yeah.
Not that one. Or the other one, what? The Drift King.
Yes.
Dory King. That's the one.
Bukan, itu sudah positif, Pak. Zero saya selamat.
Okay. Now you just have to find out the roots. Okay. Yeah, the roots of this.
Zero, bro.
On the right side, you write down 0. Yeah. Okay. Yeah, you can do that there.
Yeah, can. Use three. Oh, let me use my calculator, bro. Sorry, I don't want Flex my calculator.
Yeah.
Ada 3.
Yes.
Ada 60, 180, and 300.
Yep.
But it start from -1.
No, itu poin asimptotnya intersect.
Itu poin asymptote intersect.
Ya, poin bunganya asimptot.
Di -1.
Yep.
Jadi yang 60 mulai di -1, yang 300 di -1, 180 juga -1.
Iya,
Pokoknya kalau nggak ada.
pusat asimptot.
That is asymptote, not the root locus. Asymptote is the direction where the root locus will go. It is not necessarily the point of root locus.
He also like there's supposed to be a line, right?
Supposed to be a line like set from
Where?
-1 to
No. There is no line. Asymptote is just a direction.
Oh, I mean like it is
So
just like
the
the
direction.
Huh?
dotted lines.
The dotted lines, yeah.
Like you can also like draw the dotted lines.
In the water activity.
Because that's too obvious.
Exactly.
Too obvious. We know already that this asymptote 180, the 180 degree asymptote, it is already represented by this location of root locus. So we don't draw the dotted lines. Okay.
At the breakpoint, the intersect point is a -1.
Yeah, negative one.
No, at the right side of -1, no has dotted line.
On the right side, this one?
Okay.
No.
Kalau ada berarti
Yeah. Later after we find out that this is okay. From this number, which one do you think that the breakaway point is? It should be this one, yeah. Huh? It will break away means you will split from here, yeah. It will split. If it is -1.5, it is here. There is no root locus there, right? Okay. Where is the? Yeah. So now we get the breakaway point here, yeah. That's the breakaway point, -0.4 something. So what happened with the root locus? Root locus will go from open loop poles to the asymptote in this case, yeah. This one is easy, okay. It will just go all the way to the left, no boundary on the left. In here, they will go one from here and one from here, go here, meet in the middle, right? Meet in the middle, and after that it will go there. Yeah, like that.
we know which one goes up. Is it from the red up or red?
No, they are the same. They are the same, so it doesn't matter.
Color, right?
Yes, of course, but it doesn't matter. Yeah, it is symmetric. Okay. When it matters, MATLAB will give you an arrow, like in the Nyquist plot later. Later in Nyquist plot, MATLAB will give you an arrow where it will go. In this case, it doesn't matter.
So the next point is -1 or
Negative 0.4. Negative 1 is the open loop pole. Open loop pole and also the intersection between asymptote and the real axis. Yeah, you see this location of -1 that we found here, Adriva computed this. This is just a point for you to place these dotted lines, you know. Let's say I have a dotted line which has a 60-degree angle from the positive real axis. Okay. Now I want to put this line where I should put it. Okay. I'm looking for that location. Based on this, I have to put this line here. And that's it. Yes. Okay. Yeah.
So then just only to put the reference point. The real line for the asymptote direction is negative 0.4.
Negative 0.4 is where the root locus split. They split. Okay, they split. Okay. Because one coming from here, one coming from here. When you increase the k, root locus will go here like this, meet here in the middle. One going up, one going down. Okay. And then if you ask which one is going up, which one is going down, it doesn't matter. Okay.
Yes, slide curve.
A slide curve like this. Yeah, because as I said, approaching asymptote is just like approaching a plateau. Okay, so it will do this. It will not. Yeah, it will not going like this. Okay. No, cannot. Have you ever seen a response of first order system? First order system, if this is the input, it will go like what? Like this, yeah. Approaching a plateau, yeah. And so in this case, you will not find a response like this. Okay, that is not a dynamical system. That's magic. Yeah. Reza, any question? Sit here. Yeah.
So when we sketch the locus,
Hey, this is sorry, this is Antonis, yeah. You bring your chair. Yeah, Fariza.
so when we sketch the locus, then we are expected to draw the rectangular line and the red line as well.
This one? Yeah. This line, that line, and also the red line. You have to compute the breakaway point and also the asymptote intersection. Yeah. Up to this drawing, that's enough. Okay. I will not ask you to draw the root locus in exam, yeah. No, I will not ask you to draw the root locus. What I will ask you is to design a controller using the root locus method. And to do that, you need to know how the root locus behaves. Yeah, the property of the root locus. Like for example, if I add another open loop pole here, how does the root locus look like? Huh? Wait. Let me draw here. Yeah? If I add another open loop pole here, huh? One here, one there, yeah. And then after that, where they will go? How many asymptote? How many?
4. Oh, no zeros. Yes, sir.
I'm cross. All of them cross. Yeah. So for example, you get that this is the intersection between asymptote and the real axis. Yeah, it will form a 45-degree angle. Okay, this will be 45 degrees. Okay. So that's the asymptote, and then it will have two breakaway points. Yeah, of course it will split here, right? And also this one will split there. It will not be half circle. It will go there, and this one will go there. Yeah. Why? Ah? No, cannot. You see, you need to understand that the asymptote is just like a vacuum cleaner. Yeah, it is a vacuum cleaner that sucks in the root locus. Okay. So the nearest point from here is going to the right. It cannot go to the left. No, cannot.
It can only happen if there's zeros.
Yeah. You see, the zero and then asymptote is just like a vacuum cleaner. You think in that sense. Okay. Yeah.
It was about Teddy's conclusion.
Yeah.
Don't you get the breakaway point?
Yeah, breakaway point.
And then I finish. So first, I will get 1 plus k. Then close loop.
This is the denominator of the closed loop.
Only denominator.
Oh, denominator of close loop.
Yeah.
And then, we isolate the k, right?
Yes.
And we derive it.
Take derivative.
We need to find the gradient of the slope.
Yeah, we get the gradient.
Oh, what?
The gradient.
This one.
The gradient of this function. Yeah. When the gradient is 0, then it will bounce back.
Oh, so we want to make it equal to 0.
Yeah. Yes.
Because we want to make it the highest power is equal to
No. This is a function of k. Yeah. Function of k in S. Yeah. This is not the roots. This is not the pole. We are not trying to find the pole. We just want to find the breakaway point there. Okay.
Then we pisah. I mean, yeah, also this.
Yeah, if it is quadratic like that, you use ABC formula. Okay, anything else? Okay, let's move on. Yeah.
How do you determine for this one then? We can directly determine it's going to be the negative zero.
Yes.
If it's going to be here, how do we determine?
Yeah, of course. If you are having the quadratic equation, then one will be here, one will be there. If your computation is not pointing to point in the middle of these two poles, then something is not right. Must be wrong.
So it must be in between.
It must be in the between. Not in between the root locus, but it's inside this real axis root locus. Yeah, it won't be here. Okay. So the same calculation, just like what Teddy did over there. Yeah. Okay, now we know that it will cross the imaginary axis. Yeah, for sure it is crossing the imaginary axis. If you are asked where it crosses the imaginary axis, yes, at which point that it crosses the imaginary axis? How do you answer that? You can answer using the Routh-Hurwitz criterion.
Well, will change sign.
Yeah, with change signs. Okay. What is the minimum value of k that it will change signs, and then once you get the value of k, you put it back here, find out the pole. That will be the location. Okay.
Use characteristic.
Yes, characteristic. Okay. Wow, this one I haven't put it in. Yeah, in this case, example number 5. This is interesting because we have 2 poles and 2 zeros. Yeah. Open loop poles. Okay. Open loop zeros. No, yeah. Angle of asymptote. No. Yeah. Yeah, numbering open loop poles. Who hasn't got turn? Fariza. Okay, Fariza. You erase this. Erase this. Tuh.
Numbering the open loopholes and
Yeah, you put the number from the right to the left. 1, 2, 3, 4. Labeling. We are we are not talking about the asymptote in there.
jadi ada apa? Ini. Ya.
Yeah.
What does the zero represent in system?
Say it again.
What does the zero represent in system?
In what zero in what system?
For example, yang tadi for this one, kan ada zero.
Terus yang
What will
ganjil
it
ke kiri lah.
translate? What will the zero translate in the graph?
Zeros, it will be the
Yeah,
The circle.
What kind of behavior will the system have regarding to this?
okay. If you have a zero, yeah, then the zero is the location of your closed loop poles. When you increase your k very large, it will approach zero.
It will approach to zero.
Yes.
The polar system will be zero
Yeah.
when it's empty.
Yeah, if you set your gain very high, it will approach zero. Okay, so that's like a terminal behavior of your closed loop pole. Okay. Yeah. Okay. Let's see this. This is okay, yeah. Anyone objection on this?
So,
Okay. Yeah. Next question. You want to ask?
tadi kan di yang tadi itu function we will want to approach the zeros and then we'll do the
Huh?
The graph will approach the zeros and then it will go to the asymptote.
No, I don't say that. If you have zero, it will approach zero. If it doesn't have, then it will approach the asymptote. So the role of zero and asymptote, they are the same role. It will suck in the root locus.
So we can say that zero is a more powerful winner.
Yeah, correct. Yeah. Okay. You have marked already the root locus location on real axis, yeah, on the left of the odd number, yeah, on the left of number 1, on the left of number 3. Okay, I want to say here that if you know already which one is the odd number, you don't have to write this down later, yeah. So this is just for practice. It is okay. Okay lah. Intersection asymptote with real axis, we don't have, yeah. What about breakaway and break-in points?
Breakaway.
Boy, it has breakaway and break-in points. It will break away here, yeah. Split here and then meet here. Okay. Yeah, do the math. Will it go like this? No lah. It has no manner. I have to say that. So this kind of behavior will not happen in physical system. Okay. So that's the location. Oh, why is it there already? I have computed it. Okay, so this is how to do it. You know that the k is a fractional function, yeah, fractional function. So you have to take the derivative of a fractional function. Yeah, you know how to do it. Yeah, you review again lah.
Like just now, yes, sir.
No, that's not a fraction. What Teddy did just now, it's not a fractional function. Fraction is you divide a function by another function. Okay. Anyone know? Bonus point? If the k is let's say f of s divided g of s. Let's say this is the f, this is the g, yeah. And so your dk over ds will be
F is supposed to be df over ds minus ds
okay.
minus e over ds
Okay. G square. G square.
Percent of product rule kan?
Itu F atau G?
Which one? This?
Iya.
G. The one that below. G square. So if you want this to be zero, we want this to be zero, right? Yeah. So which one we take? Is it the top one or the bottom one?
Bottom one.
Oh, why?
Top one lah. This will be zero if the top one is zero. Okay.
Ya.
Tapi atasnya kan kayak gitu karena
The G is important here, yeah. All right. So that's the location of the break in and break away. In the sketch, what you draw is like this, okay? Just like that. Not necessarily. Yeah.
Ya, karena situ
So you say that if we have
kita tarik sama zero.
breakaway points between the root locus,
Okay.
it will make a circle.
Breakaway point.
In the root locus,
No, that one breakaway, right?
because
ada one.
Yeah.
Let's say this come out in the exam, sir.
Yeah.
That kind of quadratic function kan
Itu paling boleh ini beda.
Yeah.
Use calculator
Dia ada
to write
line here.
negative b plus minus plus b square.
use calculator straight boleh.
What calculator?
Yeah.
Really, use calculator to
To find
find the
the root. Who has that kind of calculator? Who has? 1, 2, 3.
harusnya semua bisa.
Yours cannot. Cannot.
Oke, no.
Because not everyone have that calculator. Okay.
Iya, assalamualaikum.
But then everyone, so if everyone can, sir.
If everyone can, then okay.
Kamu mau bimbing kamu kasih boleh.
I told you that I will not give you a problem in exam that asks you to draw the root locus.
Loh,
No. But you will use your knowledge on the behavior of root locus to design a controller.
ada unit.
Okay. I'm telling you that let's say if you have a system, like this, yeah, and then you are asked to design the controller. What kind of controller that you will use to make the system stable if you are thinking from root locus point of view? Okay, what do you think? We want it to be stable. Okay, just stable. For example, just stable. Just stable is okay. If no. I'm saying that this is k of s. Okay. So the idea is that let me remove this one first, yeah. So Fariza get the point just now, yeah. So I will first draw the open loophole, yeah. Open loophole. It is at 0, both of them at 0. How many asymptote? 2, right? Okay. So it will just go up and down. Okay, one going up and one going down. So if you leave the k to be a constant, will it be stable? No. Okay. Yeah, you know without computing the closed loophole, you know that the closed loophole will be unstable for whatever k you put there. Okay, so that's the knowledge you get by knowing the root locus behavior, right? Understand or not? Yes. And what you will do if you have this, if k there, you change the k so that you at least have 0. Okay, you need to have 0 in there, yeah. Open loop 0. If not, then it will just blow away. Okay, if let's say you can put the 2 0 over there, let's say for example, yeah, if you can make it like this, then this will go there for sure. Okay, yeah, it over here is all stable. You can choose any point there, it is stable.
Back then we get the value of a by putting our mouse point of.
Yeah.
How do we do that?
How do you that? You choose a point there. Yeah.
Below the key, right?
Yeah, you design a controller by having the, let's say the 0 over there. You design it to be -5 and this -7, let's say. And then by establishing this situation, you explain to me that there exists a controller that can stabilize that, and that's fine. Now in the exam, I will not ask you to do a very complicated computation. Yeah, only your understanding on designing the controller. Okay, if it is too complicated, you have to use MATLAB.
So when we design a controller, define what key is.
Yeah, the KS is.
When we define KS according to the stable part of the system.
Yes.
And like there's a range of k where it's stable.
Yeah, in this case, if this is happen, yeah, then any k positive. Sorry, if your system is k multiplied by a controller over there, yeah. This is a gain, and this is the controller, and then your system is 1 over s squared, like this, yeah. Then you can set your gain k to be any number if that's the situation. Okay.
But just now Nathan was asking like how, for example, like what the camera it has to be on the intersection.
Yep, on the intersection.
Yeah.
Oh, there is a formula, is it?
Find the K without method.
Yeah. The formula.
Oh.
Intersection formula.
Yeah. Coba-coba tadi.
This is the break-in point, right?
Oh yeah, it's a formula.
You know what the break-in point? You know what's the S, right? Yeah, you know what's the S, and then you plug in S in there, you get the K. You can find the K from there.
Yes.
Now in the homework, what did I ask in the homework?
Is there a possible value?
Yeah, I'm just asking the possible value for K, right? Whether your system is stable, unstable, over them, under them, critically them. Okay, wait. In this case, is there any K? Do we have K, the gain K, yeah, that makes the system to be over them?
Yes.
Yeah, in what location is that? It's in here, yeah. When the root locus are distinct, then you have the overdam situation. Critically dammed? Yes, you have it here, right? The underdam, it's all over here, yeah, the complex. So that's the answer, right? I'm not asking you on what's the value of K to make that happen, right? Yeah, depending on the K value.
So di MATLAB, when you choose one gate dan another gate itu so ada asymptote kan, terus ada gate-nya, terus di kiri ada asymptote lagi. Itu gate-nya sama tapi itunya beda.
Oh yeah, of course, that happens. Yeah. Let us see here, yeah. If we see hovering in here, let's say this is the MATLAB plot, yeah. If you hover to here, it tells you again. Let's say gain is 1. Over here you also have gain to be 1. Over here also, yeah, gain 1. You will have 4 points where you have gain to be 1 because you have 4 poles. Yeah, 4 closed loop poles. So in the MATLAB you will find out same gain that will give you 4 different closed loop locations. Okay.
If one of your poles is 0, then there's a gain for each pole.
Yes, there's a gain for each pole.
There's a
We
gain
have to
for each
specify
pole.
which pole to run.
Yeah. This is what is it? We have the K of 1 over, yeah, this is S to the power of 4 plus blah blah blah, okay? Because this is 4 poles, yeah. This is 1 plus, and then we have the numerator. This is the denominator, okay? If you set one kind of K, let's say you set K to be 2, how many roots that you will have from the denominator? How many? 4, okay? You have S to be this, let's say A, S, B, S to be C, and S is equal to D. 4 numbers, right? So in the root locus, you will find also 4 numbers that has the same gain. Yeah, that's what happens.
The value is different.
Yeah, of course lah. If the value of this is the same, then you will find out S plus, let's say 1, S plus 3. If all are the same, then the root, you see, the closed loop location are the same.
Because in the numbers, I get qualification. Because they ask for critical in them, right? So I put the case equals to a number. But then when I check another location, the number is the same. Then it's not critical in them.
In a situation like this, and then let's say if it is like this, okay. So in here it is critically damped, yeah, like this, critically damped, and at the same time you will have another K over there where it is not critically damped, right? So in here it is critically damped for sure, and then you know which one is the dominant pole? This one, right? The dominant pole. That's it. Okay, any other question from you? You want to discuss? Yeah. Critical damp at 0. Here? No, cannot. In here, it is neutrally stable. And neutrally stable cannot.
So they're not.
No. It is not bistable. If you also have a situation like this, yeah, on the right side, like this one, is this critically damped? Huh? Not stable. Not stable, so I cannot say critically damped. If it is on the left side, yeah, then it is critically damped.
Berarti kalau dia
Is it if the order to be that if the root locus and the last question start from left, it is stable.
No. If your root locus, pay attention. Pay attention, yeah. You see, we can have a situation like this, yeah. We can have a situation like this where, okay, there is another root over there. Where is your stable root locus? Where is it? It's to the left side of the imaginary axis, yeah. So it doesn't say that if your root locus starting from the left, it always be stable. No. Stability only states that if you are on the left half plane, open left half plane, then you are bistable. So in this situation, you will have stable poles over there, and then some of them will be unstable when your gain is more than something. Okay, Stephen? Huh? Gain is the K. This K. Yeah. Yeah. Okay. Huh?
What does it mean by gain equals 1 and gain equals 1? Does it mean that gain can have
That's what Anthony just asked.
what? What's the question? What's the question?
Anthony, you explain to him.
What's the question?
So in math one, when you try to check the plot, right? And you check one gate, like one curve, and come the gate, right? And you check the other one, the gate is the same.
Yeah.
The value.
Yeah. How? What?
So explain.
You didn't listen.
If it's there, meaning that point is there.
Okay, you guys, how many this is the open loop transfer function, okay? If you make a closed loop transfer function from here, how many closed loop poles that we will have? How many? How many closed loop transfer function? How many closed loop poles? How many closed loop poles? 2. Only 2. You see here, this is 2. Yeah. You see, root locus. Let's back to the definition of root locus, yeah. Yeah, when I say something, you listen. Which is why you always skip the discussion. Root locus is the location of the closed loop poles, okay? So when we say the root locus starts from the open loop poles, that means the closed loop poles, if let's say open loop pole are 2, then the closed loop poles are also 2. Okay, we have 2, right? You cannot say we have 2 open loop poles and then suddenly you have 3 closed loop poles. Itu datang dari mana itu? Satu lagi hantu itu. It's a ghost poles in that case. Cannot, ya. Okay. So if you set K to be, let's say K to be 2, how many closed loop poles that you will have? 2. If you set K to be 100, how many closed loop poles that you will have?
2.
Also 2.
Yeah, that one.
Okay, yes. Okay, ya. Ya, cocok kau rasa ya. Oke. Okay, this example. In this example, open loop poles are not located on the real axis. Yeah, all of them, open loop pole, open loop zeros, are all on the complex number. Yeah. So there is none of them that touch the real axis. Okay, you know why? Or you want to ask why, sir? Okay. What's the reason? No. I'm asking about how does this line go?
But why is there no real axis pulse?
Yes. Why?
Because
Why, right?
because the groups of the poles are imaginary.
Imaginary.
Yeah, the imaginary. Okay. And then why doesn't it go like this? And touching the real axis. Why?
Secara simple.
No, that's actually I think it should go with the fastest route.
Okay, let us mention again the behavior of the root locus. Root locus starts from open loop pole, or it starts here, yeah? And it will end at open loop 0. So this is the end point. And the 0 act as a what? Vacuum cleaner. So it's like you are blowing blowing a paper, and then this is the vacuum cleaner. Okay. So this is the way they will go. Okay.
Even though it's in the image complex number plane,
Yeah.
also start horizontal.
Say that again.
So if the zeros, sorry, the poles are in the complex plane,
Poles complex plane, and then
root locus will always start parallel to the axis and then go to the zeros.
okay, now you are asking about the initial direction. I mean,
Yes.
the initial direction is not straight. As you can see, this is not straight. Okay, it has a direction up a bit, and it has an angle.
Do we know how to compute that or find that out?
You can compute that, which I will discuss now. Okay. Yep. No asymptote, yeah. Angle of asymptote, none of them. We don't have to number, yeah. There is no real axis poles and zeros. Okay. So I have several items in here. You see, we are actually relying on this, yeah. Although I never explained about how it's all being derived, but all of the characteristic of the root locus starts from this characteristic equation. Yeah, I'm saying that the root locus is the closed loop poles location when k is varied from 0 to infinity, and then root locus is also all s satisfying this equation. Okay. So without having to follow the rule, if you can find s satisfying this, that's the root locus. So randomly picking s, is it here? You plug in into this equation. Is it -1? No. Find another point again. No. If it is yes, then that's the root locus. You get what I mean? You don't understand. Okay, sorry. Let me give an example. Okay, an example. Yeah, let's say 1 plus GH is 1 plus K times 1 over S plus 1 lah, like this, yeah. Okay, so we know that we have open loop poles in here, okay, 0 minus 1, and then also we know that it has a closed loop pole over there, and then later on it will go there. What I'm saying about a GH to be -1, like this one, yeah. So that means this is the GH, okay. So you have K over S plus 1 to be -1, okay. So you plug in S from here, S you put there, okay. Can it be -1 with some K? Yes or no?
Yes.
Huh? Yes, because it's there.
Oh, yeah.
If I take S from here, Now you take S, let's say -2. You try -2, yeah. You have K over -2 times. What does it become? K divided by -2. This is minus.
Satu dong.
Huh? Okay, 2, yeah. 2 equal to -1. Can we have a positive K that can make this happen? No. So that's not the root locus position. Okay. No root locus over here.
Itu perlu digambar juga.
No need. Okay, yeah. So this is how we test it. We take a point, test it there. Okay. Trial and error.
What is stopping us from putting K?
What?
What is stopping us from putting K?
We don't want to have K to be negative. We want K to be positive. The gain is positive, man. Yes.
If we put S equals to -1, cannot add because the root locus range from -1 to 0.
Yeah, just your K will be 0 in that case.
Example in 0.5.
Try.
Minus 0.5. You try. Yeah. S.
S.
Yeah.
Bisa sob. Kan sob itu dikali sob.
Iya.
Okay, minus 0.5 plus 1 will be
Minus 0.5 plus 1 become
plus 0.5, and then you multiply by minus 0.5. It becomes 2.5. Okay, you do that. Equal to, so what's the K in this case? Yeah, this one multiplied by this become a K, right? Yeah, K will be 0.25. Yes, that's the K. So we have K. So K is positive.
Oh, because the K become negative.
Yeah.
Oh.
Okay, yeah. So that's how we can do. Okay, but this method, of course, this is a trial and error method, and so all of that rules are all derived from that condition actually. Yeah, and then we can split the condition into two. The first one is the magnitude condition. The second one is the angle condition. The one that we use so far is the angle condition. Okay, this is a bit confusing, so pay attention carefully. Okay, we are saying that GH has to be -1. So the angle of GH must also be -1. Okay. The angle has to be -1. Okay. Now, how do we get the angle of a transfer function?
That formula.
Yeah, of course, this formula lah. You see, a transfer function have its imaginary part and also the real part. Okay. If you take the tan inverse of the imaginary divided by the real, then you will get the angle itself. Okay. Yeah, because the angle condition is -1. -1 is our real part, and the imaginary part is 0. Okay, because the imaginary part is 0, then we know that we are looking of an angle that has a tangent value of 0. It is 180. 180, and it's odd multiple. Okay. Odd multiple mean 180, not 360, 540, etc. Odd multiple. You multiply by 1, by 3, by 5. Okay. So in that case, the sum of the angle must be 180 and it's odd multiply. So you can check the the test point. Yeah, we will have a test point. Let's say in this case, our test point is here. Okay. So, what will be this angle? 180. What will be this angle here? 0. So 180, right? Yeah. The angle of this test point is 180. So all of the points in between these two is 180. Yeah. Oh, this is not the. Yeah. Is there any laser pointer that also a marker? Huh? What if we have the tip of this marker to can fly away? If I press a button, shooting Steven going here. Okay. Yeah, if we test over here, what will be the angle?
180.
Yeah, from this pole it will be 180. From this pole, so the total angle is 360. It doesn't satisfy. Okay.
Wow.
Okay. Yeah.
When are we going to use this?
Huh?
The exam.
No, we use it already. We use this angle condition already. Okay.
Sir, I don't understand.
Yeah. Yeah. Which part?
Yang barusan
Okay.
Itu ada example.
Yeah. Okay. Let's look at the left figure first. Okay. We have open loop poles here. Yeah, and here. P2, P3.
F3, sir.
Hmm?
You want the next one?
Which one? We have 4 open loop poles here. P2, P3. P1, P4, and then 1 open loop 0 here. Okay, this is a test point. Yeah, how do we get the angle? You get the test point first, and then you connect the test point to each of the open loop pole, open loop 0. So you have how many lines? 4 lines. Yeah.
How do we get the test point, sir?
Yeah, it's up to you lah. You take the test point.
Test point is from the car.
Huh?
Test point from the car.
For the what?
Okay.
No.
What for?
Test point is just a test point.
What for?
For you to test whether that point is it a root locus or not.
Oh.
If the test point satisfy the angle condition, then that's the root locus location.
Okay, sir. I have a new question.
Yeah.
When do we use magnitude check and when do we use angle check?
If you cannot find the root locus by using the rule, yeah, the rule that we just discussed, yeah. For example, when we are encountering this, we cannot use those rules, right? You see what I'm going to say?
Those rule is
Those rule is whether in the real axis it is on the left of the odd numbered poles and zeros. Okay, which one?
The one set yang kiri.
No, it's the angle condition.
No, I think even this part. So how about like overbreak your unstable and in that bookshelf?
No, this is another question again. No, this one I haven't finished yet.
Oh, isn't that like
No.
Oh, yeah,
That's not likely to check.
okay. So we have 3 ways to check for S. Or just 2 ways.
2 ways lah to check for S.
Magnitude and angle.
Only 2 ways, magnitude and angle.
So
Okay.
this one that we do from yesterday is
It's all the collection of rules based on the magnitude and angle condition. You don't understand, yeah. I keep it for the last explanation so that you know already. Okay, this is the behavior of the root locus, and now I arrive at the basic theory of how those rules are being derived.
Oh.
Okay, those rules are being derived from here. This is the theory. Wait. Where is it? Okay, so you see, when we are answering example 5, let's say, okay, we know we can mark location of root locus on the real axis. Okay, that is based on the angle condition, magnitude condition. But I haven't told you yet. Okay, I only tell you that this is the location of root locus. Yeah. And then also the intersection, those are coming all from the magnitude condition. Okay. Breakaway, break-in points, we are exploiting this. Yeah. Okay, you say? And we make an equation where k is equal to a function of s. That's coming from this condition. So if we are encountering this problem, we know already that the zero is a vacuum cleaner, right? So it will just suck in. And so to get the angle, we do this, yeah. Take the line from the test point, and then the angle is measured from the positive real axis, which is why this is the theta 2, and this is V1. Okay. All angle coming from the poles, we will mark it as negative, and the one from 0, we mark it as positive. Okay. So let's say, for example, this one, the one that we have the example number 6, yeah. Let's say our test point is over here, yeah. The angle, the first angle is 90, yeah, 90, so 180, okay.
Yeah.
And then this angle over here, 360, 360, yeah.
Oh, we follow the dotted line.
Yeah, the dotted line, 360 or 0, the same, yeah. Let's say it's 0. 0 is also acceptable, okay. So we have 180, yeah, 180 in here. What about this? Is this 0? No, it cannot be 0, right? So if it is non-zero, then this is not a location. So in that case, you can move this somewhere so that the total angle is 180. Yeah. Okay.
Understand also. Understand now. Understand.
After I do this.
Understand. So we try to manipulate the value so it
Yep.
180.
Yeah.
Oh,
Nggak harus sama.
Oh, iya, totalnya
Oh, iya.
Out multiple. Yep.
Itu 180 karena dia
Exercise. This one actually is for the homework next week. I think it's next week, yeah. Homework next week. Next week Monday. But let's just hover for 5 minutes. Yeah, additional 5 minutes. Where do you think the closed loop pole will go? Number A.
Oh no,
It's just a sketch.
3 poles.
3 poles.
means 3 asymptotes.
3 asymptote, correct.
It goes.
Just go one there, and then one go to the left. Okay. Okay.
Oh yeah. Yeah. I bet. Yeah.
Oh, ini? Okay. So in here we have 2 poles and then 2 zeros. What happened? Yeah, 2 poles in here and 2 zero. Asymptote. Circle?
Goes from.
Goes from 0 to
Directly
Yeah, one to the right, one to the left.
Yeah.
And that's it.
That's it. Yeah.
Yes. Okay.
Is it how we should answer this one?
Yes.
Yes, it's like that.
Yeah, you just draw it going to the right. This one go to the left.
We cannot use the rule.
You can. We are just using the.
2 and 3 can same.
Yeah, 2 and 3 is the same spot.
So for me this is distinct.
Huh? Which one? B? Yeah. This number distinct, yes.
Sir, why suddenly have to go to the right hand? That's it. From poles to zero. From poles to zero. Yeah, so
And number
polesnya ke zero.
Oh, but is that how is
I
that?
know Locus.
Huh?
Apa taruh Lucas? Oh, sudah zero.
Yeah. Zero is sucking in the root locus. Number A, yeah, it goes to the asymptote.
Oh iya.
Yeah.
Satu dua
Yang di nomor
tiga
ini
kan?
Hah?
Satu dua. Terus yang tiga sama empat. Nanti dua sama tiga posisi sama.
Oh iya.
Jadi garis-garis aja.
Apa yang di nomor itu yang Lucas doesn't have to be
Kalau di posisi
as long as the X go to zero.
Okay, number A. Number A, what happened just now is that everything is at zero, yeah. So you have asymptote. This is 60 degree, and then another root locus going to the left. Okay, that's exactly what will happen. And then problem B. This is 2 poles. We number it. Okay, number it. 1, 2, 3. This is 4. So on the left of number 1. On the left of number 3. Okay. Huh? Why? Why it has to be a circle? It's got to the zero already, you know. No. Yeah, that's the circle. If it is reached zero already, then what? You sketch the root locus. Yes. Testing? No. If you don't know, if you do not know where's the root locus location by using those rules, then you use the test angle. Okay. Yeah, one position.
Okay. Say for question A, we'll get 4.
4. Okay. Yeah.
There won't be any result.
Of course there is lah. There is. Okay, the question from Chris. Question number A, but then we have 4 poles. What will happen? How many asymptote? 4. Okay, this is 45 degree. Yeah, this is the root locus. That's the root locus already.
And we say the asymptote is the root locus.
Yeah, because you will depart definitely from here, from 0. Okay?
You don't have you don't have breakaway points. You don't have breakaway points because all your poles have the same.
They are all starting from here.
Go to the left. But that's number 4. So I cannot go to the left.
They are all starting from here. There is no root locus on the real axis to the right, real axis to the left. No. We don't have.
So for the B, have angle or not?
Ah?
For the B, angle or
We don't. We only have this. There is no. The first thing, there is no asymptote. Okay, and then the root locus goes from open loop pole to the open loop 0. Okay, and then root locus location is on the left, now odd numbered. Okay, on the left of number 1 we have here. On the left of number 3 we have here. Once it reaches the 0, the root locus will not go anywhere. Just going home. Okay. Going home, take a sleep. Tomorrow wake up again.
no asymptote.
No asymptote.
So no go direct.
No.
But that have asymptote because no zero.
Yeah.
Oh.
Okay.
So then the poles at the same location.
Yes, which is this one.
So gitu.
Okay, you still want to continue or we just stop here? You have something to go? No, it's up to you. We can discuss the next if you. You have other class?
I have FYP with one.
Yeah, sure. I'm saying sure. No. Sure. Okay. Yeah.
Also one person.
Yeah.
One more.
Okay. Just one more, yeah.
One more slide.
What about this one?
To the left, berarti.
It is on the left of the odd number, yeah.
Yeah.
So we will have here and we will have here. Yeah.
Circle.
So there will be a circle coming like this. Okay. One goes through there, one goes to the right.
Left of the circle.
Left of the circle. Yeah. What about this?
This one number one.
Three asymptote. The first asymptote is 60, 180, and then 300. Okay. Then we need to find out what's the intersection, yeah, to the real axis.
Yeah.
Okay, in that case. Yep. Okay. Just one more. You think of a reasonable function, reasonable number that you can compute. Let's say the easiest one is maybe -1 plus minus 1i. That's easy, right? Yeah, easy. So you have this, that one. Oh, okay. Starting from there. So one definitely is there. Yeah, going to the left. Okay. So this one cannot go like this. It's impossible, yeah, because one of the asymptote has been used by this. So the only thing that will go for the asymptote is these two. 60 degree. Yeah, assume it's over there, so it's just go there.
Red line.
Oh. Red line.
Yeah.
Red line. Ya, tergantung.
Karena mulainya dari situ.
It starts from here, but yeah,
Posisi breakaway-nya sama sekali.
I don't know where does the the intersection is. Let's say in the intersection just passes through this, yeah. Then it's just straight line. If let's say over here, let's say, yeah, like this, then it's a curve, but the curve goes like this, okay? Yeah. Yeah. We cannot go there, of course, cannot.
They were already past it.
No more crossing here. Okay. So that ends the class. We'll see you again on next Monday. Sudah siap semua? Sudah? Ada yang ngantuk nggak? Berdiri dulu, berdiri. Senam sore. Ya, handphonenya taruh dulu handphone. Put down your smartphone. Oke, yang pimpin senam siapa yang pernah di pabrik? Ya, stop, pimpin senamnya stop. Senam dulu stop. Ayo senam. Ayolah.
Lagunya dulu.
Gak ada lagu. Iya, gimana lah? Hadap sana. Ya, senam. Ayo, peregangan tangan dulu, tangannya ke depan. Yuk, ke depan. Yuk. 8 hitungan, 8. Ke atas, ke atas.
Oke, 1, 2, 3, 4, 5, 6, 7, 8.
Kanan.
Kanan, kanan.
2, 3, 4, 5, 6, 7, 8.
Bisa.
Oke, oke.
Sini.
Aduh, kecil amat.
Ada lompat. Gini dulu.
Oh, belum. Oh, belum. Oh.
Ini, balik. Nah, balik. Satu, dua, tiga, empat, lima, enam, delapan. Ini. Satu, dua, tiga, empat, lima, enam, delapan. Ayo, atas.
1, 2, 3, 4, 5, 6, 7, 8.
Sekarang kakinya, guys. Ayo,
Aduh, kaki. Oke. Aduh, jatuh.
Sampingkan. Ayo, nafas. Belakang. Bisa. Lagi.
Satu, dua, tiga, empat, lima, enam, tujuh, delapan.
Satu, dua, tiga, empat, lima, enam, tujuh, delapan. Gantian lagi. Nah, sekarang lari di tempat. Aduh, tempat.
Ayo, come on.
Dua,
Ini futsal ini. Oke. Nampak.
sering.
Oke, yang tadi di cut ya, jangan dimasukin ke video ya.
Bagi videonya tadi.
Nah, ini mic-nya belum dulu lagi. Udah, nggak ikutan ya.
Besar.
Turun dulu kau.
Ah.